Dear friends, today we'll continue with studies on dynamic equilibrium. So, before deriving the conditions and equations for dynamic equilibrium, let us study some basic definitions. Basic definition of the important parameters involved in the dynamic equilibrium. So, first comes vibration. Always remember earthquake force, they are cyclic in nature. They produce oscillations, to and fro motions. So, with to and fro motions, two type of definitions they come into picture. One is vibration, second is oscillation. Vibrations, oscillations. Both indicate to and fro oscillatory motions, to and fro motions. But if there is deformation of structure during reciprocatory movement, it is called as vibration. If there is deformation of structure during reciprocatory motion. Reciprocatory means to and fro motion. Then it is termed as vibration. If the motion of the structure is reciprocatory without any deformation, then this is termed as oscillation. Very simple example which I have seen earlier, pendulum bob. The bob does not deform, hence that motion is called as oscillation. But if you strike a use type this thing with a rubber pad, that is called as vibration, because there is deformation of the body. In oscillation there is no deformation, only to and fro motion. Next important is free vibration. Any body can be set into vibration by an external force. So usually we call that as excitation force. Once the vibration is set and external force is withdrawn subsequently, it is stopped, external force is stopped, then that type of vibration initiated in the structure is called as free vibration. Hence, vibration of system which is initiated means started, which is initiated by an external force which is subsequently withdrawn, subsequently stopped. Hence, this vibration is called as free vibration. Next comes forced vibration. The type of vibration where external force is involved during the vibration. So external force is not withdrawn, but it continues to act on the system. External force is involved during vibrations. Next comes damping. In real life structures, when they are subjected to vibration, the structure tries to resist it. Due to this resistance, the amplitude of the vibration goes on reducing with respect to time, and the amplitude goes on reducing indicates that there is dissipation, there is reduction in vibration energy of the system. So this process is called as damping. When the subject is, when the structure is vibrating, the amplitude of vibration goes on reducing with time due to dissipation. Dissipation means release of, decrease of, dissipation of vibration energy. This process is called damping. In case of free vibrations, where external force is removed after initial excitation, the motion gradually evens out. Evens out means stops. Now this damping, it depends on a lot of factors and it is very difficult to quantify. It is very difficult to measure the damping. Hence, damping of this system is represented by a viscous damping force. Let F naught be the damping force. This F naught is equal to C into X dot, where C is damping constant, X naught is velocity of the system, velocity of the body going into motion. Hence, this force F naught, which is damping force, is represented by viscous damping. Next comes important parameter, degree of freedom. Any body, any mass, it can have 6 displacement components. So 6 displacement components are delta x, delta y, delta z. So similarly, it can have 6 rotations, theta x, theta y, theta z. 6 displacement components. The number of possible displacement components of a system is called as degree of freedom. The number of possible displacement components is called degree of freedom. Hence, degree of freedom represents minimum number of coordinate system involved or required to donate the position of mass m at any given instant of time. So here very important term is at given instant of time. Now, coordinate system, depending on coordinate systems, we can have different type of degrees of freedom. So first is SDOF, single degree of freedom. It means only one displacement component is sufficient to describe the movement of the system. Second, MDOF, multiple degree of freedom. Third, continuous system. Now to derive equilibrium equation, we need to make an analytical model of dynamic system. So considering all the forces acting in a dynamic system. So any analytical model of the dynamic system, 3 elements are very important. So first element is mass represented by m. Second is spring constant. that is represented by K. Third, damping, that is represented by C. So first let us look at each of the elements. Mass M signifies the mass as well as inertia characteristic of the structural system. So mass includes mass of the system and inertia characteristics. So inertia is given by m into a, mass into acceleration. So inertia force is equal to m into x double dot, where m is mass, x double dot is acceleration, and that is given by d square x by dt square, where x is the displacement. So 2 times integration of displacement gives us acceleration. So second component is spring element. Spring element signifies potential energy and stiffness characteristics. Spring element signifies potential energy and the stiffness characteristics. Stiffness characteristics means elastic restoring force, the force which tries to restore the system back to its original position and this thing. So restoring force depends on stiffness. Restoring force is equal to K into X, where K is stiffness of system, X is displacement of the system. Third is damping element. So damping signifies energy dissipation. Vibration energy is gradually lost. Damping signifies energy dissipation. So damping force is given by C into X dot, where C is damping constant, which you need to identify or evaluate for the given system. X dot is velocity, and that is given by dx by dt. Usually damping is represented as equivalent viscous damping. Next important parameter of analytical model is external force. Let that external force be F. Always remember, this external force is function of time. Function of time means the properties of external force F varies with time. Let us continue our studies to draw or to find dynamic equilibrium conditions. Let us consider a single bay, single story rigid frame, which is a SDOF system. Example, consider a single degree of freedom system. I am going to consider a single bay, single floor story, rigid story. Now certain assumptions are made here. So assumptions. First, the mass of the column is very small as compared to slab and beams, hence neglected. mass of columns is neglected. Second, beams are infinitely rigid. Beams are infinitely rigid. Infinitely means very, very rigid. They do not deform. Hence, stiffness for the system is provided by stiffness of the columns only. When the frame vibrates due to lateral load in the horizontal direction, the forces acting are the forces acting in the frame due to lateral force are: first, external force, that is f of d, force f function of time t. Second, inertia force. So inertia force is the force which is trying to oppose the movement, that is given by m into x double dot, mass into acceleration. Third, damping force. The vibration of the systems eventually subside, eventually reduce, and they become zero. So this process is called as damping. So certain damping forces are acting on the system, and that is represented by c into x naught, where c is the damping constant, x dot is velocity. Fourth, restoring force. Every system tries to maintain its own position. So there is some certain spring element acting into that, or the stiffness of the system, and that is represented by k into x, where k is the stiffness constant, x is the displacement. Now let us try to draw a diagram representing dynamic equilibrium. Let us consider a body like this. Let these are the two columns. This indicates stiffness K or spring constant. This indicates damping force. So same which I am going to consider for external force, I am going to change its direction for my ease of consideration. So same system, I will be considering it like this. Let this be mass m, stiffness K, damping force C, damping constant C. Let this be subjected to force F of T, force F. Assume that there is displacement in x direction like this. Now we will try to write all the possible forces acting on this mass M. Say this is external force F of T. Next, there is some inertia force which is trying to oppose the movement, and that is given by m into x double dot. So similarly, there is some spring action which is acting, and that tries to restore it back to its original position. So opposite to external force, that is k into x, stiffness into x, displacement. Again, there are some damping forces which tries to reduce the amplitude of the vibration, and again that is opposite to external force, hence this direction c into x dot. So these are the all the forces acting on the dynamic system, where x is displacement of mass with respect to ground. X dot is relative velocity with respect to ground. X double dot is relative acceleration of mass with respect to ground. Now let us write the equations for equilibrium. First, equation of motion for forced vibrations. Forced vibration means external force is acting. So that m into double dot x dot plus c into x dot plus kx is equal to f into t, function of t, ft, where m x double dot indicates inertia force, c x dot is damping, kx is stiffness, and f of t external force which is acting during the vibration also. So this we call it as forced vibration. So forced vibration is a system where external force is acting during the course of vibration also. Second, equation of motion for free vibration. Equation of motion for free and damped SDOF. When I say free vibration, it means external force does not exist after initial excitation. You excite the system and remove the external force. Hence, external force F of t is 0 for free and damped. Damped means damping exists. So F of t is 0. Hence, external force F of t is equal to 0. So equation of dynamic equilibrium will be m into x double dot plus c x dot plus kx is equal to 0. When the external force or excitation is absent during the motion, it is called as free vibration. Such a motion is initiated by imparting some initial displacement by a force and immediately withdrawing it. Let us consider third case for undamped and free vibrations of SDOF, single degree of freedom system. It means free vibration means external force F of t is 0. Undamped means damping is also 0. Hence, force F of t is 0 and damping is 0 means C into x dot is also 0. So substitute these two in generalized equation and get the equation of equilibrium. So equation of equilibrium will be m x double dot plus kx is equal to 0. So this is the equation of equilibrium for undamped and free vibration. The motion is considered as undamped when energy dissipation characteristics are 0, when damping is 0. A dynamic system under ideal conditions should not have any damping and it should continue to vibrate at same amplitude throughout. However, the system has some own damping characteristics due to frictional loss, due to which there is dissipation, there is reduction in energy. Hence, the amplitude goes on reducing and eventually it comes back to its original position. So these are the three equations of dynamic equilibrium for three different cases. So this is the case for forced vibration, where external force is acting throughout the vibration. Next is the case for free vibration, where external force is removed after initial excitation. Next is undamped and free vibration, where damping constant is 0 and free vibration means external force F of t is also 0. So these are the three equations. 1, 2, 3. Thank you.